Alright, what is going on? So I'm going to dang, my interest is so bad. I don't know how to start the videos. I hope I figure out a good way to start videos eventually. But so what I'm gonna try to do for this problem is whoops, what's going on? So I have not read this problem. I don't know what this problem is about yet. So I'm about to find out. But this is the daily problem for today, June 19th. So let's read it, record the start time. So my strategy here will be, I'm going to show how I'm going to approach this problem, how I'm going to come up with a strategy. Hopefully that goes really well, and then I'm going to try to code that. So here we go. So given an array of citations sorted in ascending order, each citation is a non-negative integer of a researcher. Write a function to compute the researcher's h-index. Okay. According to the definition of h-index on Wikipedia, a scientist has index h if h his/her n papers have at least h citations each, and the other n minus h papers have no more than h citations each. Whoa, what is this talking about? Okay, let's maybe analyze this. So let's try to understand the h-index. Has index h if his or her n papers have at least h citations. So you have n papers, like maybe you have, and then I'll put a number of citations. So these are the number of citations. So he has 1, 2, 3, 4. So this person has n equals 5, which is a number of papers. So he has 5 papers, and we set n equal to 5. Now we're going to say that it has index h if he has at least h citations each. Have at least. So at least means that you could have more, but the minimum you could have is this. So the minimum, I think h is equal to 10. That is, he can have, if you look at all his papers, they have at least h citations each. Each one has greater than or equal to 10 citations. So I think that's what it's saying. And the other have no more than, and the other n minus h papers. What? So then you take 5 minus 10, which is negative 5, have no more than h citations each. Okay, well, let's look at their example, because that is a weird system. I've never heard of this system. What is the purpose of this? Interesting. So, okay, I'm not going to go too much into reading about that, but let's just read here. So citations are equal to 0, 1, 3, 5, 6. And basically, I have an output of 3 right now. But yeah, so I have the citations equal to 0, 1, 3, 5, and 6. So let's look at this example. I think I'm going to have to work through an example. So like I have no approach yet because this is a little bit confusing to me. Okay, output is 3. So he has 5 papers in total, 5 papers, and each of them had received 0, 1, 3, 5, 6 citations respectively. So he has 3 papers with at least 3 citations. Okay. And the remaining 2 with no more than 3. Her H index is 3. So they have no more. So then 2 papers with no more than no more than 3 citations. This is very bizarre. So basically, if I look at this, if you look at 3, 5, and 6, right? So you take 3, 5, and 6, and you say, well, these have at least 3 citations. So then take n minus the 3, and you get 2. So you need to have 2 papers with no more than 3 citations. So using 1 would have not worked, because 1, there would have been 4 papers. Actually, wouldn't 1 work? So 1 would work as well. So what if we considered h is equal to 1? Then what we would do is we would say there are 4 papers with at least 1 citation, and there's exactly 1 paper with no more than 1 citation. Another thing is, so you want to return the highest H index, so that means we can't go larger, so we can't go to 5, because, I mean, it's kind of obvious, you can't, so if you go to 5, 5 won't work, because 5 minus 5 equals 0. Papers with no more than so yeah, 3 has to be equal. So for instance here, since the value is 5, you need to have 5 papers. So one problem here is when you use h equals 1, do you have wait, is that a problem? If even you have at least a citation each and the other, I don't think there is another answer. It says here if there are several possible values, but there's not several possible values here. And why is there not several possible values? Is because if you say h is equal to 1, right, that means you need to have 1 paper with at least 1 citation, and the rest have no more than 1 citation. But this is false, because you have 3 papers that are higher that have more than 1 citation. So yeah, this is a follow-up problem to H index, where citations is now guaranteed to be sorted in ascending order. Could you solve it in logarithmic time complexity? So that might help. So okay, so first off, what's my initial strategy? Okay, so what I need to consider is, so I feel like one thing you want to do is sort the array, which is going to take n log n time complexity. So once you sort the array in ascending order, I feel the answer is going to be based on the number of papers. So I think, would a binary search work? I think you can maybe do a binary search on a sorted array. I think mostly the challenge would be figuring out how the binary search is going to work, which is what we'll do here, because like this is my basic strategy. I think a binary search will work, and that would allow us to do the log time complexity, and this is important because this is how you could solve it for the follow-up, right? So this is dealing with the follow-up. Okay, so if we were to use a binary search, okay, so what I'm going to do now is, because this is going to be really bad, I'm going to maybe not record this and then come back and record once I start getting a better idea. But yeah, this is what I'm going to do, and then I'm going to start coding. So I'm going to start figuring out how the binary search will work. But I think a binary search will work because you basically take the mid, and see if it's... Alright, What's going on? Returning to this video, I'm going to show the code. So I finally got the code to work. I'm going to go over what I learned from this problem. So basically, I didn't really understand the problem when I read it, I guess, because when it says at least 8 citations, that means that means at least h. Like, it doesn't have to be equal to the value of the element. Well, that doesn't really make sense now. Let's first explore what my binary search is doing in their basic example. So 0, 1, 3, 5, 6. So first off, left is equal to 0, right is equal to the n minus 1, which is n is equal to 5, so it's 4. And then mid will be equal to 2. First thing we notice is that, hey, n minus mid is equal to 2. And we say citations mid is equal to 3, right? So we say, okay, well, the value is larger, right? So citations with 2 is equal to 3. But 3 is greater than n minus mid. Now, what does this mean? We can say that after, since this is order, after 3, we have n minus mid citations that are at least greater than 3, right? Which is true, right? We have 5 and 6. And we have exactly 3 of these because n minus mid is equal to 3, my bad. So we know we have at least greater than 3, right? Yeah, that's correct. So we're going to save this as one of our answers. And so we want to find something larger, so we're going to move our so we're going to save h equals to 3 right now. We're going to move our right pointer. So now our left is still equal to 0, but our right is now equal to 1. And so our mid will be equal to 0. And so at this point, citation, so n minus mid is equal to 5, and citations 0 is equal to 0. So in this case, we can't say, since the citation value is 0, we cannot say that there are at least 5 more elements, because there's 5 more elements from where you're currently at. We cannot say that they all have a value of at least 5, because first off, the element you're looking at right now is less than 5. So we would have to say, well, we need to move to the right. So if you move to the right, you would basically get left equals, you move the left to the right. So we get left equals to 1, and right equals to 1. So mid is equal to 1. N minus this mid is equal to 4, but again, the citations at 1 is equal to 1, which is less than 4. So of course, we cannot have 4 elements in the array with at least 4 citations, because we have one here that is less than 4. And so here, we would basically move the left pointer again, but we'll go out of bounds when we do that. So it's going to end, and it'll return the 3. So that's a nifty problem, but let's look at this edge case where we have 11 and 15, because this is kind of interesting. Okay, so left is equal to 0, right is equal to 1, mid is equal to 0. So let's see what happens. So n minus mid is equal to 1, or 2, I mean. Right, so the length minus the mid is 2. And then we say citations mid is equal to 11, right? So in this case, where we say citations mid is equal to 11, that 11 is, well, that's way greater than 2. So we can say at least we have 2 elements with at least 2 citations or more, because we know that the next element after it, all the next elements after the 11 are going to have more citations. And we know that we want the h to be equal to the number of elements that have at least that many citations. So we know h has to be equal to 2 here. So we set h equal to 2, and we're going to move our right pointer. So we say left is equal to 0, and now right will be equal to -1. So actually we stop. There's no point to keep going. And a little bit more about why do we move the right pointer here. So the left pointer is good. So it works for these examples, right? And I mean, if you have an example where like you have 0, 0, well, basically this is never going to update h, because the n minus the mid is always going to be greater than the citations, than the number of citations. So you're just going to return h equals 0. So that's why we have h equals 0 here. Let me go into time complexity real quick. So time complexity for this is going to be n log n when we sort it, and then once we do the binary search down here, that's just log n. So this kind of answers the follow-up question, which is if this problem was already sorted, then the time complexity would be logarithmic. But because we have to sort it, we do get n log n. Maybe there's a way around that. Maybe I can... Okay, well... honestly, what happens if we do that? It actually works. So I guess this problem is already sorted. So that would be if it's sorted, we would do that. If we assume that they're not sorted, we do this. And you notice the runtime is changing slightly slower. It's not making too much of a difference. But yeah, you can see we don't actually need this for this problem. I guess they are sorted. So yeah, this really is a log n runtime. And whenever we update h, we do n minus mid, because when we're updating it, it's always that length. H is always equal to the number of elements, including the element you're currently at, that number of elements from where you're starting. I don't know how to say that, but yeah, one other thing that I was going to look at is so I looked at those two examples. I think the 11-15 example might help really with explaining what's going on. You can also look at 100, right, and say 100 is an example edge case. Well, what should 100 return? Well, if we think about it, we know that the number of elements that we can have is 1. We can have at least one element with at least one citation, because 100 is greater than 1. We can't have 2 because we don't have 2 elements in the list. We only have 1 paper in a sense. We don't have 2 papers, so we can't have h equals 2. So at best, h could equal to 1, and that is what this returns, actually. So I hope that kind of is a okay explanation for this problem. It was a pretty good problem to apply binary search method. It took me a little longer than I was hoping, but yeah, it was a good problem overall. So yeah, cool. Let's go.